Welcome everyone to MBSE 2.0 for Interfaces, presented by Mark Simons. My name is Donna Long and I will be your host during today's webinar. Mark Simons is a principal systems engineer at Vitec Corporation, where he is responsible for consulting and training functions. Mark has over 25 years of experience in the systems engineering of space, aviation, telecommunication, and defense systems. He has received multiple awards over the course of his practice for his previous work at MITRE and NASA. Mark has also taught topics in systems engineering for the Johns Hopkins Whiting Engineering for Professionals program. Before Mark gets started, I have just a few housekeeping items. We will be answering questions at the end of the webinar. Please send your questions in as soon as you think of them through the question tab on the webinar control panel. Mark will answer as many questions as he can today, but if we do not get to your question, we will reach out to you after the webinar. The webinar is being recorded. If you experience connection problems during the live presentation, a recording will be available within 1 business day. The recording will be published to Vitec's webinar archive located on our website. At the conclusion of this webinar, a survey will open on your screen. Please take a moment to give us feedback on today's presentation or on what topics you would like to see covered in future webinars. Now I'm going to turn the presentation over to Mark. Welcome, and thank you for joining us.
And thank you, Donna. Thank you for that introduction. To get started, I want to remind us that last month, David Long presented on the power of MBSE 2.0 and what it means to achieve the intended level of performance that we set out to do with MBSE. Today, I will focus on MBSE 2.0 and what we can achieve with engineering of our interfaces. So in MBSE 1.0, we missed the mark with our first attempt. We still did not close all the silos in our organization. Our world is still more complex than when we even started with MBSE. We have more complexity in the systems we're building, and our organizations are more transdisciplinary in nature. We have a higher coupling with engineering, and we're missing the mark by not being able to communicate effectively throughout the organization. We forgot about the context of our system and our development environment, and we ended up creating a new silo of system engineering with a methodology that could not effectively communicate our knowledge. And that's the key detail here with our system engineering and model-based systems engineering, is we want to represent our knowledge explicitly in detail, and we need to be able to communicate that more effectively. Diagrams really don't really do this for us. It only is a partial solution to the communication. We still have a lot of information in organizations that's implicitly understood and ad hoc of nature, and we need to be a little more systematic and methodical about how we exchange that information. So what we see in 2.0, what we can achieve here is a level of a performance where we're integrating multiple voices within our organization, a variety of different stakeholders. So we're being able to close those gaps with the transdisciplinary domains and nature of our organization. We achieve a more concurrent engineering design. All the engineering disciplines and system engineers and engineers are able now to work from a single repository of information, and they're better integrated in manners that they can understand in their own domains. The design is communicated also in 100% explicit detail. There is no room left now to have this implicit design of an implicit set of information. And in addition to the design, we're also able to kind of record information about our journey. The issues and the rationale for the decisions that we make are better captured. And weaknesses in the design can be traced back through verification and validation. So in a word, MBSE 2.0 is really based on information and sharing that information, whereas with 1.0 we would just had a subset of that information, the information that was captured in our diagrams and stored in our repositories. So what we see though is that MBSE 2.0 is really furthered and enabled by what we call a systems-metamodel. The systems-metamodel is an information model representing all the entities and ideas of information that we have in system engineering, and verification and validation. We have a natural language that we use in the systems-metamodel, and it's based on an entity relationship model of information. The systems-metamodel is industry proven, and it has stood the test of time, and it's the basis of our products here at Vitech. So why is the systems-metamodel so important? Excuse me. Why do we emphasize the nature of the systems-metamodel? Well, essentially it can help us communicate more effectively. In a 1.0 model-based system engineering environment where our information is stored essentially in the information in our diagrams, it makes it difficult to communicate. We essentially have a model to human interface and exchange of information. We exchange information with documents. Now the documents are generated from information in our repository. We've definitely made that advancement, and we can even share models with our engineering counterparts. But to the extent that they can understand the models and the extent that they can interpret the documents, we still have some gap that is incomplete and prone to error. And this is the gap we're trying to close in model-based system engineering 2.0. So with model-based systems 2.0, our MBSE repository is based on a schema now that's based on the systems meta model. And with that, we are now better to integrate in a kind of a model-to-model environment. We can export information from our database in a manner that's consistent or can be transferred easily into other design tools that the engineers are using. And ultimately, we would have, say, APIs that could connect directly with the tool itself and in a seamless manner so that all of the information available in our system engineering design is available to the electrical engineer or the mechanical engineer. So with the systems meta model, we achieve seamless integration of information and we reduce our errors. And so that's what this is all about. And the rest of this, I'm going to be talking now about how we apply this to interfaces. So I can't underestimate the importance of interfaces to system engineers. We all know, we're all taught that risk is at the interface, and we do a lot of work to try to manage the interfaces. We have interface control documents that document the details of the interface and the specifications of the interface. We have interface requirements that help us understand how we want to build that interface, and we have processes that in place to help us manage those interfaces and make sure we reduce risk. But before we get into this, what is an interface exactly? There can be a lot of loose talk when we refer to interfaces in our meetings, and as we discuss the issues at hand, how can we sharpen our understanding? And so we do that with the systems meta model. But before we get there, I want to start to motivate these definitions by looking at the existing definitions that we have of interfaces today. What I don't want to repeat and read each of these definitions, but they are a representative sample of the definitions that are available to us in the community. But what I want to really point out is that there's a lot of inconsistency in the way the definitions deal with interfaces. In one case, the definition refers to a place. In the second place, it's considered a boundary, and also maybe as a hardware or software component. or maybe a connection between two or more components, or maybe it's a system element itself. So you can see that we get a lot of confusion and inconsistency about interfaces, even in the definitions that we're used to and use. So we don't really know when we're speaking one to another which definition we're really working with. So how do we deal with this? How can we sharpen this up? Well, we have these items, this notion of interfaces defined in our systems meta model in MBSE 2.0. And what we do is we define interface as the notional logical connection between parts of an architecture. So what we see is that the interface is dealing with the definitions that are logical and abstract in nature. And so we can also organize these interfaces in a hierarchy, so we can have abstraction layers of interfaces themselves. But interfaces are always notional and they're always abstract. The really key aspect of this meta model in MBSE 2.0 is that interfaces can now be related to links. In fact, you really ought to relate them to links to make the definition more complete, because we now know with those definitions that there are some physical aspects to our interfaces, so we can't just deal strictly with notional concepts. So that brings up the next item, the link. How do we define what is link? How is a link defined in the systems meta model? It's defined as a physical implementation of a connection between parts of an architecture. So that's the real key difference, is that it's physical in nature. It can be abstract, but it definitely can be concrete. And we can make certain abstractions by creating this hierarchy of links in the same manner that we could create hierarchies of interfaces. So at the higher layers of our link hierarchy, we become more and more abstract, and at the deeper layers we become more concrete. So let me just show you now what the system meta model looks like with regard to interfaces and links. It's essentially an entity relationship model where we have key classes that we use in the discussion of interfaces. Interfaces and links I've already defined. Components are those physical elements that we're trying to connect and join. Components have ports, and links transfer items, and I'll explain how all this works. But I just wanted to point out that there are relationships between each of these entities. So I mentioned that interfaces can have hierarchies. Well, you would express that in your MBSE model by using an includes relationship. Here I'm showing up in the upper right hand side. We have the interface, and it can include other sets of interfaces. It is also comprised of links. So this is how we relate the interface to a link. And links themselves also have hierarchies, so they can include other links. And so just through this simple nature of the systems meta model and the relationships that are allowed to be created, we can be very explicit in our description of an interface. Interfaces are joined components, links connect to components. It's just a way to make a distinction there between the type of connection they have. And I'll get into how components will expose ports and how links transfer items. But this is the fundamental nature of how our systems meta model works. So let's take a look at this from a point of view of an email exchange. How does the systems meta model play out? Well, first of all, we can see that we will have first two components, a workstation on either end. We have a sending component and a receiving component. And what we do is we can define a notional interaction between these components as an interface. We could call it the email interface. But this is just notional. We know that there's more detail to this interface, but sometimes it's useful to refer to this as the email interface. But when we require more detail, when we're talking about this interface with maybe a different community of users, we may need to refer to more of the physical connections that really create this interface. So here I'm notionally depicting them as these links, these physical wires, cables, Ethernet connections that connect the computer with the routers. And you can see there's a chain of these links that take us from one end of the sending workstation to the other end on the workstation. And so this helps us understand the connection between interfaces and links. These interfaces, these links all comprise this interface. So I'm trying to use that natural language that's there in the systems meta model. Now the one thing that I did not mention was the item. And that's the email itself. How do we model that email? Typically, we just use the email as an exchange between the two components. But with the systems meta model, we have a richer understanding, a more explicit understanding of how this email works. It's actually being sent through the link. So what we see items being transferred through. And so now we have a much richer way of describing our interface. We have a much richer vocabulary that we can use when we are talking with engineers and stakeholders as we discuss elements of our system design. So how does this all look now in an MBSE tool such as Genesis? Well, we can represent the logical interface here on the left by showing a generic interface between the email sender and the email receiver. And then on the right, we can represent the physical links as those Ethernet cables that are now connecting the sender machine to the router, to the network, to another router, and then over to the other workstation on the other end. So we can represent interfaces and links here both logically and physically. Now what I'm not representing here on this slide here is the item. The item is represented in behavior, and I'll get to that later in the presentation. But going back to how now we've defined our interface, we can use the meta model and the way that the information is organized in our MBSE repository. We can query that information and look for more insight from our model. We can now look at all the interface, all the relationships our interface has. We can see how it joins the email sender and how it's comprised of the Ethernet cables and how the Ethernet cables are connected to the routers. And we begin to see a closure here of how we can go from email receiver to email sender through our cabling and links. So going back now to just the basic notion of a link, we can see that links map very well to the physical entities in our system design that relate to, say, standard interfaces like Ethernet cables, HDMI cables, inline fuses, you name it. These very simple basic cables map very well to links, and you can see how we can express them in our system design. We can have the HDMI cable connecting a computer with the monitor, or the Ethernet cable connecting the computer to the switch. But what if we want more detail? What if we have maybe something that's a little bit more complicated? Take the example of a cord connecting our power to our appliance. We can see that we need a three-phase cable, and we can model that here on the upper right as a single link to show how we connect the power panel to the appliance. But we know that maybe a three-phase link power cable has some extra detail in it that we want to express. Like on the lower left, we see that this power cable is full of 4 wires, and sometimes those wires are important in our detailed design to understand how those are routed. So we may want to take those individually and use the hierarchical nature of links to express that the three-phase cable includes links for grounding and hot wires. Excuse me. Okay, and we can also take this now to an extra level of detail when we get to the design details of our components. If we want, we can actually get to the point of expressing physical ports on our components, exposing those ports as we use as the system meta model describes. And then we can connect links to those ports so we can show exactly how the wiring is lit up or affected, say, in a detailed design of how a wiring harness is put into an automobile. We have an extra level of complexity here that the systems meta model allows us to model effectively. Now, there will come a time when you're presented with some complexity that requires you now to look at your links, not so much as connections, but as also physical entities. And as you recall back to our definitions, there were many definitions that referred to links and interfaces as physical components in our system design. And in some cases, we will see that, and we will have to be cognizant of that and recognize when we can use links and when we will have to use components to model parts of that interface. And so in this case, I'm showing a car bus, a controller area network similar to a local area network that's connecting different electronic control units within our automobile. And you can see there's different cable segments that will be used to connect those ECUs with the bus. And so this is just one example of how we can use components in conjunction with links to model an interface. All right, so up till now, we've been looking at interfaces and links in isolation. And what I want to do now is take a look more of the workflow. How do we do this as engineers? And so I want to bring out three more items, three more classes in our systems meta model. We have the notion of requirements, notion of functions, and the notion of functions. And you can see requirements here specify almost all the items here. They can specify components, ports, interface, links, and items. But when it comes to functions, we have a special relationship because we want to be able to show that requirements are the basis of a function that now is allocated to a component. So now we can also associate functionality to the components. And you'll also notice that the functions have an input-output relationship with the item. I've described earlier how the links transfer the item, but it's really key point to understand that the functions are also, or that the items are also related to the functions. So let's put this into a workflow. Let's first take a look at developing requirements. That's one of the first steps. And if we have, we use our tools now. In this example, I've created a requirement called flashing lights. And the description here is the system shall have flashing lights. Very simple, but it's representative of the work that we do to define our requirements. And we can use the requirement class to define this element. Then the next step would be to define our behavior. So now we're working with our tool to represent this diagram representing our behavior. The information is in the tool itself. It's represented in the schema of the database. I'm just showing you here a reflection of that information that's represented in this activity diagram. So you can see I've defined some functions here, sending a flash signal, receiving a flash signal, turning a light on, turning a light off. And you can see there's a flow of functions. Now what's also on this diagram are the items. The flash signal is an item that is output from the send flashing signal and input into the receive flashing signal. And the light signal, light on signal and the light off signal are outputs of the turn light on function and the turn light off function. So now this is the origin really of our items. And we can think now, okay, how are these signals transferred through the links in our system? So that brings us to structure. And we can kind of see it represented here on the left. We can see that we have a body control module, a type of electronic control unit, and we have lamps and we have light switches in our automobile. And we see that now we have them connected through links that are being represented here by these wires. And now let's try to map these requirements that we've defined through our links and through to the links. And we can query our database, our systems repository, to understand the relationship that we've created for that flashing light requirement. We can see that we've made it a basis using the systems meta model. We've made it the basis of these functions of sending flashing signals and receiving a flashing signal. And we can use the systems meta model to allocate those functions to the components, in this case, the body control module and the light switch. And we can also show now that we have links that connect the body module and connect the light switch. And what we can see too also is that these links are transferring these items, the flash signal, the light on signal. But the key here is that that these items are all related in our system design. We can see that the component that's reflected here on the left in our schema, the data that's in our database, is also the same item that's represented in our physical design, and our links are also the same. So they're one-to-one relationship. So we have in our MBSE repository a fully consistent 100% explicit representation of the information in our system design. But what we can do now with MBSE 2.0, and this is where we really get to the power in general of the systems meta model, is we can now work to export our MBSE information to this and export it for use in the engineering domain. We can have, in this case, we have a query box, dialog box that allows us to represent any information in our repository that's organized based on our systems meta model and export it out to a spreadsheet. And then we can take this spreadsheet and import it into an electrical design tool. All we do is map apples to oranges and make sure that the meta models are aligning with each tool. And the more that we can converge on a similar meta model, the better off we are with this exchange. And then ultimately what we want to do is take this to the next level and build out application interfaces where we can have our tools automatically interacting and sharing information so that we have access to all the information in our database, not just here, just the physical design, but the requirements and the functions and the behavior. And so this really gets back now to the whole purpose of MBSE 2.0. We want to get a more integrated engineering design. We get that by exchanging information, and we can exchange information effectively and efficiently with 100% explicit detail with an effective systems meta model. Excuse me. And now we've achieved MBSE 2.0. We've broken down those silos. We are better able to communicate our ideas. We can work in a transdisciplinary nature, and our systems designs help us deal better with our complexity. So some final thoughts. Systems meta model enables our MBSE 2.0 level of performance. It addresses interfaces in a complete manner, and it integrates information effectively with stakeholders. So that brings me to the end of my presentation today, and I'll be happy to take questions.
Thank you, Mark. We do have a few questions thanks to our participants. I encourage you to join the discussion now and submit your questions using your webinar control panel. If you do need to leave the webinar, please take a moment before you go to respond to the quick survey that will pop up on your screen. Our first question comes from James. How do you layer interfaces in a hierarchy?
Very good question. There's a lot of rich detail that you can put into your system design by making effective use of an information or of an interface hierarchy. Typically what you do is you'll have interfaces defined at the very highest level of your system design. So think about your context diagram, your high level context diagram that you're drawing, so that represents the interfaces between your system and your external interfaces, external components. Typically those system context diagrams can get very busy because, as we know, we have a lot of links. There are a lot of physical connections that we make, and it's better to represent all that information through interfaces. And so at the very highest level, we want to be able to represent a single interface with a single external component. But we know that things are going to get more complicated. We know that we're going to have, say, electrical interfaces. We're going to have mechanical interfaces. We're going to have data interfaces. Even that level of detail is going to be too complicated for one single high-level diagram. So what we can do is we can begin to relate in, the categories of interfaces, if you will, to a higher level interface, so that we can now begin to organize and categorize our interfaces. And what I like to do is to organize those interfaces in a way that, with an eye towards the ICDs, the interface control documents that I know I'll need to write, because essentially that is the interface that you're trying to design. So you won't get to a full level of detail, maybe as deep of layer in your interface hierarchy as you will with your design hierarchy, but for a couple of levels of your abstraction, you'll want to understand how those interfaces relate to your interface control documents, and then you can organize them in an abstract way at the highest level for your context diagrams. Hope that addresses your question.
Okay. I guess it's a follow-up question. How do you know when to stop layering interfaces or links?
Good question. So with links, it's fairly straightforward, because you're going to stop when you reach the physical level of your system design that's adequate. So if it's a standard interface, there's no reason to kind of go into the details there. You can stop at a single HDMI cable. But if it's maybe a more customized cable, or you'll want to go into more detail of how that is constructed, because that now becomes some item that needs to be assigned to an organization with your organization to supply. And so you would go to that level of detail. Now on your interfaces, again, you would stop just about the point where you are not going to write any more ICDs. So you'd have to look at your subsystems and say, well, am I going to have subsystem interface control documents? Very likely you will. When you get down to your assembly or your components, likely not so much.
Okay, we have a comment from Christopher that says, in talking about decomposing, he always advises stopping when you know the design engineer can take it from there.
That's a really good rule of thumb. But that gets to the point of, like, when is there too much detail there in your MBSE design, and you'll have to think about that when it comes to non-standard interfaces.
Okay, Christopher does have a question. He says, when producing diagrams, specifically in Core, is it possible to show links and interface elements on the same diagram?
Good question. I'm thinking.
I would probably go with hierarchy.
Yeah, okay, that's the one. In that hierarchy diagram that I showed, the little spider diagram I showed earlier, when you can look at an interface itself in a hierarchy, and it will show all its connections. It will show what it joins, the components that it joins. It'll show all the links that it's comprised of. Now, in a interface block diagram, you're only going to see interfaces. In a physical block diagram, you're only going to see the links. So that's a good way to separate concerns in a way, so that you know what you're looking at physically when you're looking at things in a more notional manner.
Right. Okay, well, thanks, Mark. That wraps up the final Q&A for today's presentation. If you have any other questions or comments, please don't hesitate to send Mark an email, or you can post your questions and comments on our LinkedIn group page. Just visit linkedin.com and search for Vitec Corporation. Thank you so much for attending today's webinar. Look for our next webinar on our website. Remember that at the conclusion of this webinar, a survey will open on your screen. Please take a moment to give us feedback on today's presentation or on what topics you'd like to see covered in future webinars. Once again, thank you for joining us and have a wonderful day.